All right, so yesterday we were going over not yesterday, day before yesterday we wrote a test. Day before yesterday, we were going over simple harmonic motion, the basics of simple harmonic motion. And we said that in order for simple harmonic motion to occur, something has to oscillate back and forth, okay? There has to be a restoring force, that is something that brings the object back to its equilibrium position. That restoring force has to vary linearly with displacement from equilibrium. That is, it has to get bigger in a linear fashion as you go away from equilibrium. Right? All of those things have to be true, in order for simple harmonic motion to occur. So what we're going to look at today is what makes that happen. Okay? What makes this force increase linearly? Looking at the energy involved, the kinetic, the potential, elastic potential energy is something we'll introduce today. Starting to lose my patience. Okay. So we're going to look at Hooke's law. I introduced that right at the end of class yesterday, just kind of briefly talked about it, but okay, we didn't really go into a lot of detail. Okay, we got to look at energy, mechanical energy being conserved in simple harmonic motion. And we have to understand that potential energy in simple harmonic motion is elastic potential rather than gravitational. Okay, I mean, in a pendulum, it's still gravitational potential energy. There's no elastic potential energy in a pendulum. But for a mass on a spring, or something on like a bungee cord or something like that, then we have elastic potential energy instead. Okay, so Hooke's law. Hooke, remember, is the guy who built the first microscope and discovered cells, okay, and then handed it off to biology. Okay, he's also the person who discovered how simple harmonic motion, or essentially the restoring force that makes simple harmonic motion works. Okay, and he did this with a very simple experiment where he had a spring hanging from a hook. Right? He knew how long that spring was. And then as he added mass to it, he measured how far the spring stretched, okay, based on how much force, in this case the force of gravity, was pulling on the spring. And what he discovered was there was a linear relationship between the amount of force and the length of the spring. If he doubled the amount of weight on the end of the spring would double in length. Okay, so they were related somehow. Okay? He also discovered that different springs stretched different distances. So there was also this other factor involved that was somehow related to the nature of the spring, which he called the spring's constant. Okay? Every spring has a different spring constant because each one of them has a different strength, essentially. Right? If we're comparing, like, a spring from a pen versus a spring from a car, they have very different spring constant. One is very, very heavy. One is very, very light. Okay? If I hung, 500 grams from a pen spring, I'd stretch it irreversibly. Okay? If I hung 500 grams from a car spring, it would change it not even in the slightest. All right, so here's what Hooke discovered. He discovered that the force in a spring, in this case the restoring force, was equal to the spring constant, the stiffness of the spring, multiplied by the displacement of the spring. So how much longer the spring would get from its unstrained length or from its equilibrium position. Okay? Now, the spring constant is just a number measured in newtons per meter. Okay? So it's how many newtons are required to stretch the spring by 1 meter. Okay? Simple spring constant. But he put this negative in here. We talked about that yesterday. What's the purpose of that negative? George?
Is it because of the when it's with the elastic band, hold it back? No, I remember.
You're totally on the right track. It's what?
It has to pull the other direction.
It has to pull the other direction. Okay? Remember, X in this unit stands for displacement. Don't ask me why. Why can't we use D? I don't know. Okay? X is the displacement from equilibrium. So when I hang these weights on the spring, they are displaced downwards. But the spring is pulling up. Okay? Therefore, we have to have a negative in there to ensure that force, which is a vector quantity, is pointing in the right direction. Okay, so the negative has to be there. Okay, so so it is a linear relationship. Everybody okay with that? Yes? Okay. So Hooke's law, super easy to use. Okay. Any problems that you run into, like problem-solving problems that you run into with Hooke's law, are basically just going to give you force and displacement, or force and spring constant, and ask you to calculate the displacement or something like that. Like they're pretty straightforward questions. Now, if I stretch a spring, what does the spring gain? Potential energy. Right. Okay, and it gains potential energy because stretching it requires me to do work. Okay, how do we calculate work? Force times distance, right? Okay. This force is this force. Okay, it's the restoring force. So when we do work on a spring, okay, we are taking the restoring force, the average in this case, okay, so K times X, and we're multiplying it by a distance, another X. Everybody with me on that? Okay, but we have to remember that this is a linear relationship. So I can't just use my maximum force. Okay, I have to use my average force. Okay, because that force times distance actually says average force times distance. So the average force is how much of the maximum force? Half. So when I calculate the average force, I take 1/2 K times X, or 1/2 Kx. Okay, is that formula on your formula sheet? It is. That is the formula for elastic potential energy. Okay? And it looks like that because it is average force times distance. Okay? That's how we calculate work. And work is a change in energy, in mechanical energy. Okay? So when I stretch a spring or I compress a spring, I'm putting elastic potential energy into it as a result of the work I do. All right, everybody okay with that? All right, so where would a oscillating spring have the most elastic potential energy? Okay, if it's oscillating vertically, yes, the lowest point. Okay, what if it's oscillating horizontally? So it's just going back and forth like this. Most stretched position, or compressed. Yeah. Okay. Remember, a spring is going to stretch out, be very long. Okay, and so it's going to have a potential energy there. But it's also going to come back and pass equilibrium and compress the spring on this end. Okay. At both of those points, the speed of the mass on the spring will be 0, right? Because it's slowing down. The spring is pushing against it as it compresses. It slows it down, stops. Okay? And then as it goes past equilibrium this way, the spring pulls on it, slows it down, stops. Okay? So in both of those positions, the potential energy is at its maximum because the kinetic energy is 0. Right? If the velocity is 0, it can't have any kinetic energy at those points. Now, similarly, as the object passes through equilibrium, the spring is neither stretched nor is it compressed. And because it's at equilibrium, its displacement would be 0, because displacement's measured from equilibrium. Okay? So as it passes through equilibrium, it has no potential energy. But it's moving its fastest, so all of its energy is kinetic at equilibrium. That's where it would move the fastest. Okay, so if we imagine this again, as the mass is moving in and compressing the spring, it slows down. Comes to a stop when the spring is at its maximum compression. Then the spring accelerates it, pushes it back towards equilibrium. Okay, and it accelerates towards equilibrium. right when it gets to equilibrium is when the spring is not stretched, not compressed, and has no more displacement. It's at equilibrium. That is where it has been accelerating the mass to, okay? All the way to that point. That's where the mass moves the fastest. And thus, all of its energy is kinetic at equilibrium. And then as it passes equilibrium, the spring starts to pull back on it, slowing it down, converting that kinetic energy back into potential, just like a roller coaster. A roller coaster goes up and down the hills, it converts potential into kinetic. As a spring oscillates back and forth, it converts potential into kinetic. Okay. All right. So, this is much better than Mr. Coderre's arm. Okay, it's a diagram. Yeah. Okay, so at equilibrium, okay, the spring, is unstrained. That means not stretched, not compressed. So it has no potential energy. X is 0. Okay, as I pull it away, according to Hooke, the force of the spring will pull back towards equilibrium. Okay, restoring force is always towards equilibrium. Right, so it pulls against me and I build up elastic potential energy. Okay, if I compress the spring the other direction, then it wants to push back towards equilibrium. And again, I'm putting elastic potential energy into the spring. But every time it gets to the equilibrium position, it's not pushing or pulling. Okay. All done, Kate? All right, everybody okay with Hooke's law there? Right, and then this is what we were just talking about here, putting elastic potential energy into any object whose shape can be changed, or object that can be deformed, and then wants to go back to its original shape. Right, so a bow and arrow, prime example. Right, when you draw back a bow, you squeeze the ends of the bow together. Okay, that stores elastic potential energy in the bow. The bow wants to snap back to its original straight shape, okay? And when it does that, it will pull the spring forward, okay, which will propel the arrow out of the bow. Everybody with me there? Okay, so the thing we have to realize about this this potential energy formula is that if it's dependent on X, at equilibrium, there will be how much potential energy? 0, because X is measured from equilibrium. So at equilibrium, X is 0, therefore there's no potential energy at equilibrium. Okay. And then K obviously still dependent on the spring, right? If I have a really light spring, it doesn't store very much potential energy because it's easy to compress and stretch, versus a heavy spring can store a lot because it's much harder. Okay, so this works just like our problems back in Unit 2 on roller coasters. Okay, we still say that for conservation of energy, initial mechanical equals final mechanical. Okay, that's initial potential plus initial kinetic equals final potential plus final kinetic. All that changes is instead of having mghi, we have 1/2 kxi squared. Okay, that's what changes. We replace gravitational potential energy with elastic potential energy. Okay. Questions on how that works? Okay. So we'll go through a few examples just to make sure everyone gets it. Okay, so I want you guys to write this one down. We're just going to quickly go through this one. This is just a very, very basic Hooke's law question. When Noah comes back. Okay, so just quickly write this one down. Very basic Hooke's law question. Okay. So this spring has a spring constant of 30 newtons per meter. So they just gave me K. spring is pulled a distance of 1.5 meters from its equilibrium position. So they gave me X. Okay, what is the restoring force? Okay, so restoring force equals negative K times X. All I have to do is plug in my numbers. So negative 30 times 1.5 is going to be negative 45 newtons. Okay, but I have to have the negative on that answer. Okay. I have to assume the number they gave me was positive. They didn't tell me whether it was left or right that it was pulled. Okay, so I have to assume my force is opposite. Okay, now Hooke's law and law of conservation of energy problems give you very similar data. Okay, they're going to give you spring constant, they're going to give you displacement. Okay, the differences here are that Hooke's law questions are only ever going to talk about one position. Okay, a law of conservation of energy problem, by its nature, needs to compare two different places. Okay, so it'll be saying, here's our initial and here's our final positions. Okay, it'll be comparing those two, whereas a Hooke's law question will say, at this spot, do this. Okay, and then we'll only be talking about one place. All right. Those are just like ridiculously easy. Do a different one. Okay. This is a tricky one. I want you to write it down. We're going to walk through it together. So we got a spring hung from a hook on a ceiling, so exactly what Hooke did. Okay, a mass of 510 grams is attached to the spring. The spring stretches half a meter. What is the spring constant? Okay, so on a question like this, let's look at our givens here. They give us mass, and they give it to us in grams. We're comparing forces here, so what should it be in? It should be in kilograms, right? Okay, so 0.510 kilograms. And it gives me X, 0.500, okay, meters. And it wants me to calculate K. Well, Hooke's law says that the spring force, or restoring force, is negative K times X. Where am I supposed to get the force from? It's gravity. Gravity is what's stretching the spring. So since the object's not going to accelerate, it's just going to hang there, the net force is zero. Force of gravity is pulling down on the mass, force of the spring is pulling up on the mass with an equal force. Okay, so they offset. So what we have then is that the force in the spring equals the force of gravity. Right? So now at this point, because I know they're numerically equal, I don't even have to worry about this negative part. Okay? I'm just solving for K. K cannot be negative or positive. Okay? It's the nature of the spring. It works in either direction. So K will never be a negative number. So if you ever get a negative number for K, you just forgot a negative somewhere and you just put down the absolute value. Okay, so we're going to have K times X equals M times G. Well, now I can do this. I know what M is, I know what G is, and I know what X is. Now I can solve for the spring constant. Okay, so I divide both sides by X, okay, and I would have 0.51 times 9.81 divided by 1/2. So 0.51 times 9.81 divided by 0.5. All right, so this has got a spring constant of 10 newtons per meter. Very often, Hooke's law will be in conjunction with gravity. Okay, if you've ever gone to like the grocery store and gone to the produce section, they have those scales that hang, okay? They use Hooke's law, right? You put something in the big dish and it pulls down on a spring, okay? Just like what we just did here. The force of gravity and the force of the spring balance, and then the dial tells you what the mass of the object inside is. Okay, so it just uses Hooke's law. So very often, the context of a Hooke's law question will be a hanging scale of some kind, or a hanging spring of some kind. Okay, any questions on that one? All right, now the other thing that we need to understand here is that in a Hooke's law question, the object could be oscillating. It could be going back and forth. If something is oscillating on a spring back and forth, okay, it's the force in the spring that's causing it to move. Is its speed always changing? Is the speed of the mass always changing as the mass oscillates? Yes, it is. So is it always accelerating? So sometimes a Hooke's law question will ask you to calculate acceleration. As long as it's not a vertical spring, okay, as long as it's a horizontal spring, the force in the spring is the only force that's acting on the mass. Thus, it is the net force, right? This is sum of all forces. The only force acting on an oscillating mass on a spring is the spring. Okay? That would mean Kx equals m times a. You get your acceleration. Okay. No, I don't want to do that. All right, let's look at number one. Write number one down, and then we're going to walk through number one together here. So, the key thing here is that this is a horizontal frictionless surface. Okay? So if it's horizontal, gravity's not a factor. It's frictionless. There's nothing else acting on this mass except for the, what's making it go back and forth? The spring. Okay? So the only source of any force is the spring itself. So that means that the restoring force is thus the net force. It is the thing causing the object to accelerate. Okay? So in that case, then, we have that negative k times x equals mass times acceleration. Right? So they want to know the mass's displacement when its acceleration is 4.11 meters per second squared to the left, and they give us the spring constant and the mass. So we know 3 out of the 4 things for this question. Okay? And again, the reason that we know that Kx is m times a is they told us it's horizontal and it's frictionless. The only thing causing the mass to oscillate is the spring. Okay? So all I have to do is solve for x. So I'm going to bring negative k over to this side. Okay? And that's going to give me x. So I'm going to have mass, which was 0.724, times the acceleration, 4.11, and that is to the left, so I'm going to make left negative, okay? And then it's going to be over negative 8.21. So my displacement would be 0.36 meters to the right, because it came out positive. Okay. My displacement has to be right if my acceleration is left. Okay? So the mass has moved. So here's what we've got. We've got this spring. Okay? We've got the mass. This is the equilibrium position. Right? The object is out here. It's accelerating to the left. Okay? The only reason it would accelerate this way, okay, is because the force is also pulling this way. That means that it must be displaced to the right. Because if it was here, the spring would be pushing that way, and the object would be accelerating that way. Everyone all right with that? So there's a little bit of visualization that has to go on in a question like this. Okay, let's look at number 2. Number 2 is a law of conservation of energy question. All right, so let's have you guys copy that one down, and then we'll walk through it together here in just a second. Okay, so I want to first point out how question number 2 is worded differently than question number 1, and that's why I know number 2 is a conservation of energy question, and number 1 is a Hooke's law question. Okay, in question number 2, it's talking about 2 different places in the oscillation. Okay, so it's saying the mass oscillates with an amplitude of 1.12 meters. What did we learn amplitude meant on the first day? The maximum distance. So it's saying when the spring is like totally stretched, or conversely, totally compressed, okay, it's going to be 1.12 meters from equilibrium. Okay, it's asking what is its maximum speed? Well, where does maximum speed occur? At equilibrium. So it's saying compare this position with this position, or this position with that position. It's saying compare these 2 places. Question number 1 says, what is the mass's displacement when its acceleration is this? It's talking about how many places. Okay, that's how I can tell the difference. Otherwise, they sound very similar. They seem like they give me similar information, right? But in a conservation of energy question, we're always comparing initial position and final position, okay, for this object. All right, so this is a conservation of energy question. Here's what we know. Mass is 0.050 kilograms, 50 grams. Okay, and it's attached to a spring that has a spring constant of 4 newtons per meter. The amplitude is 1.12 meters. Okay, and I'm writing A. I could also write X initial if I wanted. Okay, but I don't usually write X initial or X final if it specifically says amplitude, because it's a special X. It's the biggest X can be. All right, so I've got amplitude being 1.12 meters, and now I'm looking for what's the maximum speed. All right, so I could say VF, but again, I don't write it if it says maximum, because that's the biggest it can be, and I know that occurs where? Where does the maximum speed of a mass on a spring occur? At equilibrium. All right, so here's what I know about this position and this position from an energy perspective. The mechanical energy here is equal to the mechanical energy here and here. Because the potential it has at its maximum amplitude is equal to the kinetic energy it has at equilibrium, because it's converting the potential into kinetic. Okay? So it's back to law of conservation of mechanical energy. All right. So initially, since we're at our maximum amplitude, what's our speed here? 0. Okay? The object's been pulling on the spring, slowing down, stop. Okay? So I don't have any speed here, and I can't move any further. So I only have potential energy at my maximum amplitude. There's no kinetic energy there. And it's asking me to compare it to here, where it's at its maximum speed. Well, at its maximum speed, it would only have kinetic energy. Okay? That doesn't mean to say that this isn't still true. Okay? That's how we write the law of conservation of energy. It's just that we've decided that those two are 0. Okay? So this is like talking about the top of a roller coaster versus the lowest point on the roller coaster. saying the same thing? Right? The initial energy was all potential, the final energy is all kinetic, so I'm still saying the same thing by writing those that way. So can I calculate what the maximum speed is? Okay, how do I get speed by itself? Right, divide the 1/2 of mass over to this side. What happens to the halves? Yeah, they cancel, right? That gets me v squared. I want v. Okay, so v will equal the square root of 4 newtons per meter. Okay, so the spring constant times 1.12, is it? Yeah, 1.12 meters squared. Okay, divided by the mass, which was 0.05. Okay, when we do that, we should get 10 meters per second. Yep. Okay, so it's just law of conservation of energy, just like we did in Unit 2. The only difference is instead of m times g times h, we use 1/2 kx squared for our potential energy. All right, this is not the only day we're going to spend on this, so don't worry if you're not making sense of it today. Okay, we'll spend some time on it tomorrow as well, because it can be a little bit tricky. Okay, so a reminder that your gravitation assignments are due tomorrow. Okay, and I've had a bunch of people coming in to ask questions, so that's great. And just make sure you have them ready for the start of class tomorrow. If yours isn't done, you got 5 minutes right now, or you can work on it.